day, students. Today we continue our lectures in physics. And we talk about biological thermodynamics. Thermodynamics system. Thermodynamics is a branch of physics. It studies most common properties of microscopic systems that are in thermodynamics equilibrium states and processes of passage between them. Thermodynamics studies mutual conversions of the different kinds of energy in microscopic systems that are connected with the transmission of heat or making work. Thermodynamics laws are universal for lifeless and living nature. Thermodynamics is phenomenological science. Unlike atomically molecular theories, phenomenological ones learn general laws, not associated with concrete matter building, with the internal structure of the bodies or with the nature of the motion of the particles of which they are composed. Thermodynamic system is a totality of a macroscopic item that interchange energy in the form of heat and in the form of work with one another, as well as with an external medium. For example, it can be a cell, a heart, an organism, biosphere, etc. There are following dominant classes of thermodynamic system. Look at the picture. A, the first, isolated system, when it can exchange neither energy nor matter with its surrounding. And B, and these examples. And B, a closed system, when it can exchange energy but cannot exchange matter with its surroundings. And C, open system, when it can exchange either energy or matter with its surrounding. Living organisms are open systems, and only in separate parts of cell there can exist conditions typical for closed and even isolated system. The state of a thermodynamic system characterized by certain thermodynamics parameter. Thermodynamics parameter. And the first, intensive parameters independent on the mass or size of the system. This is density, pressure, temperature, and the concentration. And the next, extensive parameter depend on the amount of matter or size of the system. There are volume, mass, internal energy. The state of a system is said to be steady if it does not change with time. Steady states are said to be equilibrium once if their invariability in time is not due to the occurrence of some process that is external in relation to the system. Transfer of thermodynamic system from one state to another is called thermodynamic process. And we have two processes. Irreversible processes is defined as a succession of equilibrium state if the system passes from the initial state to the final state. The process is reversible if the system can return to its initial state without any residual exchange in its surrounding. Second process is it is irreversible. An irreversible process passes through a series of non-equilibrium states and is accompanied with the irreversible change. The system and its surrounding cannot be returned to their initial states. All real processes in nature are irreversible. Talk about thermal equilibrium. We have two systems, and the next will be three systems. A system with many microscopic components, for example, a gas, a liquid, a solid with many molecules that is isolated from all forms of energy exchange and left alone for a long time, moves toward a state of thermal equilibrium. A system in a thermal equilibrium is characterized by a set of microscopic quantities that depend on the system in question and characterize its state. They do not change in time. Two systems are said to be in thermal equilibrium if when they are placed in thermal contact. Their state variables do not change. And next, Zerus Law of Thermodynamics. If system A is in thermal equilibrium with system C, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system B. Temperature scales. And first of all, talk about Fahrenheit. This is one of the oldest scales and is based on the coldest temperature that could be achieved with a mix of ice and alcohol. In it, the freezing point of water is at 32 degrees. The boiling point of water is at 212 degrees. And next, the next is Celsius or centigrade. This is a very thin system where the freezing point of water is at 0 degrees of Celsius and the boiling point is at 100 degrees. And this third scale is Kelvin or absolute. 0 degrees Kelvin is the lowest possible temperature where the internal energy of a system isn't at its absolute minimum. The degree size is the same as that of the centigrade or Celsius scale. This makes the freezing point of water at atmospheric pressure is 273.16 degrees Kelvin and the boiling point at 373.16 degree Kelvin. Internal energy. internal energy is all the mechanical energy in all the components of system. For example, in a monoatomic gas, it might be the sum of the kinetic energy of all the gas atoms. In a solid, it might be the sum of the kinetic and the potential energies of all the particles that make up the solid. Heat is Q. Heat is a bit more complicated. It is an internal energy as well, but it is internal energy that is transferred into or out of a given system. Furthermore, it's in the same fundamental sense disorganized internal energy with no particular organization, random energy. Heat flows into or out of a system in response to a temperature differences, always following from hotter temperature region to cooler ones. Common units of heat include the popular joule and the calorie and heat capacity. If one adds heat to an object, its temperature usually increases. In many cases, the temperature change is linear in the amount of heat added. We defined the heat capacity C of an object from the relation. It's delta Q is equal C delta T. Q is a heat that flows into a system to increase its temperature by T. Many substances have a known heat capacity per unit mass. This permits us to also write delta Q is equal m C delta T. C is the specific heat of a substance. The specific heat of liquid water is approximately 1 calorie divided by kilogram and degree. The first law of thermodynamics. The first law of thermodynamics presents a general law of conservation of energy. It considers that possible change of the internal energy, delta U, heat Q, and work W. According to the law of conservation of energy, the transition of the system that undergoes in infinitesimal change from the initial states to the final states, the small change in internal energy, du, can be expressed as du is equal delta Q minus delta Wm. Delta U is a change in internal energy. Delta Q is small amount of heat added to the system, and delta W is a small amount of work done by the system. And the first law of thermodynamics is the change in internal energy of a system is equal to heat added to the system minus the work done by the system. Here delta W more than 0 if work is done by a system, and delta W less 0 if work is done on the system. The integral expression gives the exact area under the curves, which is equal to the work. And this work. The elementary work dW done during the expanding gas is defined as follows. dW is equal F and dx is equal minus P A dx is equal minus P dV, where F is a force, for example, exerted by the gas on the piston of cross-section area A. It's an area. P is the pressure on the cylinder walls and the piston, and dV is a change in volume of the gas. It's a change. And delta Q is equal delta U plus W. The heat delta Q transferred to the system is expanded in changing its internal energy delta U, and in the work W done by the system to overcome external forces. The state of gas is determined by means of thermodynamic parameter of state: pressure P, temperature T, and volume V. Gas in which one can neglect the forces of intermolecular interaction and the sizes of molecules is called ideal. The state of an ideal gas is described by the Mendeleev-Clapeyron equation. Look at this expression. It's the Mendeleev-Clapeyron equation. M a gas mass is a gas mass. Mu is a molar mass. This mu of gas. R is a universal gas constant, and it is equal to 8.31 joule divided by mole Kelvin. Internal energy of an ideal gas is a function of state. Depend only on temperature that follows from the basic equation of the molecular kinetic theory. And we can write this equation. It's U is equal this expression where I is a number of degrees of freedom in reciprocating and rotational motion of gas molecules. The energy change in heat exchange is determined by the quantity of heat, Q. The quantity of heat which is necessary for the body temperature rise by 1 Kelvin degree is called heat capacity, C. Total specific heat of the body, C, is connected with the specific heat capacity, is a small c, that has dimension joule divided by kilogram Kelvin by the ratio this C, big C, is equal mc. Small c is a specific heat capacity. M is the body weight. For gases, it is accepted to use molar heat capacity. The molar heat capacity is a C with the index mu. Heat capacity of 1 mole of gas, where ratio m divided by mu is equal 1, is called molar heat capacity, and heat capacity of 1 kilogram of substance is a specific heat capacity, C small c. Molar heat capacity, C with index mu, has dimension a joule divided by mole Kelvin, and connected by the ratio with specific heat capacity with this expression. Total specific heat, C, is connected with a specific heat capacity, is small c, and molar heat capacity, C with index mu, by the ratio. Look the last expression, this. And to talk about processes. And first process is isochoric process, when the volume is a constant value. Since the elementary work of gas is this elementary work dA is equal P and dV. Then in the case where A is equal 0, here we will write as from first law of thermodynamics, dq is equal du, but work is 0. Molar heat capacity in the constant volume process is equal to the ratio of du, the energy, divided by dt. Or in other expression, where we use a number of degrees of freedom, here. The magnitude C with index V is called heat capacity of gas mole at a constant volume. And this process in diagram PV, where V is a constant and P is changed, the pressure from initial stage to final. And the next process, isobaric process, when pressure is a constant. In a isobaric process, the heat added is spent both on the internal energy increase and on the work done by the gas for expansion against external pressure. In this case, the first law of thermodynamics will be written in the following way. Look at this expression. dq is equal du plus p dv. And divided by dt, this expression, and we will deduce the next step. And the magnitude of ratio dq divided by dt related to constant pressure. Defined heat capacity of gas at a constant pressure, and we write it C with the index P. The magnitude of du divided by dt is equal to C with the index V. And that is where we obtained C with index P is equal C with index V plus P dV divided by dt. Or taking into account that P and dV divided by dt is R, is a gas constant. It follows from Mendeleev-Clapeyron equation. And finally, we get Cp is equal Cv plus R. Or rewriting in other form this expression, and we get Cp minus Cv is equal R. We can see that Cp more than Cv by magnitude R. And it means that isochoric process energetically is more advantageous. This expression, the last expression, are called the Meyer equation. Meyer equation. And the next process is isothermal process. Isothermal process when T is a constant. The equation of state, it's a Mendeleev-Clapeyron equation. PV is equal nu RT. Goes into the law of Boyle-Mariotte. This equation is Boyle-Mariotte. And the first law will be written as dq is equal dA. In such case, all added heat goes into work, and heat capacity Ct goes to infinity, since dt is equal 0. And we can write this expression Ct is equal dt divided by dq divided by dt goes to infinity. And look at the diagram of isothermal process in the PV diagram, and in this all point of these curves, it's constant temperature, but this temperature less than this temperature. And the next process is a adiabatic process. Adiabatic process is a process occurring without any heat exchange with the environment. And we can write dq is equal 0. The first principle we be writing as 0 is equal dq plus dA, or dA is equal minus du. The work of the gas expansion or compression take place at the expense of the internal energy of a gas. Heat capacity in this case is equal to 0. The adiabatic equation can be deduced from the first law of thermodynamics and the condition that dq is equal 0 of this expression. Cv dt plus p dv is equal 0. Next, differentiating the Mendeleev-Clapeyron equation for 1 mole, and we get PV is equal RT, and we obtained PdV plus VdP is equal RdT, and from this we get dt. Look at this expression. PdV plus VdP are divided by R. Then substituting dt to this equation, we get this expression is the next step, this expression. And transforming the ratio here in view of the Meyer equation, we come to the equation this one, the next step, or this one, or this. But is it a transformation? And let us denote the magnitude, this ratio C with index P divided by C with index V is equal gamma. As a result, we pass the equation, that's here, this expression, and integrating which we will obtain the last expression was named as Poisson's equation, the Poisson's equation. And magnitude gamma is called the heat capacity ratio, where the gamma is equal Cp divided by Cv. And in laboratory work number 6, we try to define this gamma, this ratio, and we use resonance. Then Entropy and its properties. The directedness of thermodynamic processes is determined by entropy. Rudolf Clausius postulated that the function S depend only on the initial and the final states of a reversible process. For example, if SA and SB are the values of this function in the state A and B, a function S depends only on the initial and final states A and B of a reversible process. Look this expression where dq is the elementary heat that is absorbed by the system during small change of its state, and T is the temperature of heater. The change in entropy ds between two equilibrium states is equal to the heat transferred dq divided by the absolute temperature T of the system in this interval. The entropy is a function S of the state of system whose differential in an infinitesimal portion of a reversible process is equal to the ratio of infinitesimal amount of heat delivered to the system to the absolute temperature T of the system, and we get ds is equal dq divided by dt. The unit of measurement of entropy is joule divided by Kelvin. For an irreversible process, the system expels more heat to the surrounding and the entropy increases. ds more than dq divided by dt. Classical equilibrium thermodynamics describes systems which are in equilibrium or undergoing reversible processes. Equilibrium systems are maintained without an exchange of energy of matter. The main tendencies of the change of entropy can be formulated as and first, entropy change in a reversible process is zero. Entropy remains constant in the isolated system during the reversible processes. And we can write ds is equal 0. It means S is a constant. And a second, entropy increases in the isolated system during the irreversible processes and reach the maximum value. And we can write down this ds more than 0. And such a way, any process in isolated system is accompanied with the increase of entropy. ds more or equal dq divided by dt. Non-equilibrium thermodynamics. Living organisms are open thermodynamic systems that exchange either energy of matter with its surroundings. These organisms are able to absorb the energy nutrients, to take part in a gas exchange, to do work, to expel the products of metabolism. Thus, the viability of living organism presents the set of non-equilibrium processes. The result of such exchange of living organism with its surroundings is the achievement of a stationary state, which is characterized by the constant physical and chemical properties of thermodynamic system in spite of the absence of thermodynamic equilibrium. I'll talk about the second law of thermodynamics. Although all nature processes must take place in accordance with the first law, the principle of conservation of energy is by itself inadequate for an unambiguous description of the behavior of a system. Specifically, there is no mention for the familiar observation that every natural process has in same sense of a preferred direction of action. The second law of thermodynamics states that the heat cannot of itself pass from a colder to a hotter body. For example, it is impossible to transfer heat from a cold to a hot reservoir without at the same time converting a certain amount of work to heat. It is also impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. It can only get useful for out of the heat if heat is at the same time transferred from a hot to a cold reservoir. This means that there is no possibility of perpetuum mobile, which is isolated. Also from this it follows that a reduction in the increase of entropy in a specified process, such as a chemical reaction, means that is energetically more efficient. The second law of thermodynamics defined that a system will always tend toward its chemical equilibrium or maximal entropy. If a spontaneous process leaves the overall system's energy the same, and the entropy of the end state is larger than the entropy of the initial state, the change in entropy ds must be larger than zero. If a process occurs in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. Although entropy may decreases in part of closed system, there will always be an equal or larger entropy increase in other parts of the system. So that the entropy of the system as a whole never decreases. This fact is one form of the second law of thermodynamics and can be written as ds more than zero, where the greater than sign applies to irreversible processes and the equals sign to reversible process. This equation applies only to closed system. In the real world, almost all processes are irreversible to some extent because of function, turbulence and other factors, so entropy of real closed system undergoing real processes always increases. Processes in which the system's entropy remains constant are always idealizations. Second law of thermodynamics, law of increase of entropy. In closed system, the entropy either remains too constant, or second, grows, and third, in a state of equilibrium reaches a maximum. Other equivalent formulations. First, transport of heat from a body of more cold to a body more heated is impossible without any changes in the system or a surrounding medium. And the second, it is impossible to create periodically acting machine which all activity would be reduced to a rising of some load and cooling of the thermal tank. And the third, it is impossible to create a perpetuum mobile of a second sort. And we talk about two statements of the second law of thermodynamics. And first, Kelvin Planck's statement of the second law of thermodynamics. It is impossible to construct a cyclic heat engine that produces no other effect but the absorption of energy from a hot reservoir and the production of an equal amount of work. And the second, Clausius' statements of the second law of thermodynamics. It is impossible to construct a cyclic refrigerator whose sole effect is the transfer of energy from a cold reservoir to a warm reservoir without the input of energy by work. And the next. And this picture is illustrate of these two statements. And the next, Carnot engine. Look at the picture. The Carnot cycle is the archetypical reversible cycle, and a Carnot cycle-based heat engine is one that does not dissipate any energy internally and uses only reversible steps. Carnot's theorem states that no real heat engine operating between a hot reservoir at temperature TH, it's hot, and a cold reservoir and a temperature TC is cold. And this blue, this red, hot and cold. Can be more different than a Carnot engine operating between these two reservoirs. A Carnot cycle consists of 4 steps. 4 steps. Look at the picture. 1, 2, 3, 4. And we have 2 isothermal processes and 2 adiabatic. And first, isothermal expansion in contact with the heat reservoir. Look here. Look here. And second, adiabatic expansion after the heat reservoir is removed. Look at this picture. This is adiabatic expansion. And the next step, isothermal compression in contact with the cold reservoir. Look at this picture. And it's isothermal compression. And the last step, the fourth, adiabatic compression after the cold reservoir is removed. Look at this picture. In this cycle is designed in PV diagram. Of this. And the last point of this lecture, and we talk about heat therapy and cryotherapy. And talk about thermotherapy and direct contact and infrared radiation. And cryotherapy is cold therapy, cryosurgery, ice pick therapy, and cold spray anesthetics. Heat therapy are also called thermotherapy. Is the use of heat in therapy such as for pain relief and health. It can take the form of a hot cloth, hot or water bottle, ultrasound, heating pad, hydrocollator packs, whirlpools baths, cordless heat therapy wraps, and others. It can be beneficial to those with arthritis and stiff muscles and injuries to the deep tissue or the skin. Heat may be an effective self-care treatment for conditions like rheumatoid arthritis. Heat therapy is most commonly used for rehabilitation purpose. The therapeutic effect of heat include increasing the extensibility of collagen tissue, decreasing joint stiffness, reducing pain, relieving muscles spasms, reducing inflammation, edema, and aids in the post-acute phase of heating and increasing blood flow. The increased blood flow to the affected area provides proteins, nutrients, and oxygen for better healing. Direct contact. Most heat therapy has been believed to be more effective at warming tissue than dry heat because water transfers heat more quickly than air. Clinical studies do not support the popular belief that most heat is more effective than dry heat. Most heat results in the perception that the tissue is heated more deeply. In fact, recent studies indicate that vasodilation, the expansion of the blood capillaries, vessels, to allow more blood flow, is improved with the dry heat therapy. Expansion of the blood capillaries is a primary objective of heat therapy. Heat therapy increases the effect on muscles, joints, and soft tissue. Heat is typically applied by placing or warming device on the relevant body part. Never breeds of heat therapy devices combine a carbon fiber heater with a cordless rechargeable lithium battery and are built into the specific body wrap for targeted heat therapy. Such devices can be used as an alternative to chemical or plugged-in heating pads, but have not been shown to improve the clinical benefit. All devices primarily provide heat to promote vasodilation. Infrared radiation. Infrared radiation is a convenient system to heat parts of our body. It has the advantage of the direct contact in the radiation can hit directly the area where the blood capillaries and neurons terminals are. When heat comes from a direct contact source, it has to hit the external layer and the skin, and the heat is transferred to the deeper layer by conduction. Since heat conduction needs a temperature gradient to proceed, and there is a maximum temperature that can be safely used, around 42 degrees Celsius. This means lower temperature where warming is needed. Infrared is a part of the electromagnetic radiation spectrum comprised between 0.78 micrometers and 1 millimeters wavelength. It is usually divided into three segments. Segment A. It's from 0.78 to 1.4 micrometers. Segment B, from 1.4 to 3 micrometers. Segment C, from 3 micrometers to 1 millimeters. Infrared radiation is more useful than the visible radiation for heating our body because we absorb most of it compared to a strong reflection of visible light. Penetration depth of infrared radiation in our skin is dependent on wavelength. The segments A is the most penetration and reach some millimeters. And so segments B are penetrations into the dermis about 1 millimeters. Segment C is mostly absorbed in the external layer of the epidermis. For these reasons, the infrared lamps used for therapeutic purposes produced mainly A radiation. And Mechanism of action and indications. Heat creates a high tissue temperature, which produces vasodilation that increases the supply of oxygen and nutrients and the elimination of carbon dioxide and metabolic waste. Heat therapy is useful for muscle spasm, meglia, fibromegalia, and contracture bursitis. Most heat can be used in the abscesses to help drain the abscess faster. A study from 25 showed heat therapy to be effective in treating leishmaniasis, a tropical parasitic skin infection. Heat therapy is also sometimes used in a cancer treatment to augment the effect of chemotherapy, of radiotherapy, but it is not enough to kill cancer cells in its own. Heat therapy is contraindicated in case of acute injury in bleeding disorders. Tissue with severe lack of sensitive scars and in a tissue with inadequate vascular supply. The use of heat therapy for deep-seated tissue can be treated with shortwave, microwave, and ultrasonic wave. This is produced in high temperature that penetrates deeper. Shortwave produce a 27 megahertz current. Microwave use 915 and 2466 megahertz, and ultrasound is an acoustic vibration of 1 megahertz. The way ultrasonic waves work is they selectively superimpose the incoming wave and increase the energy for absorption. And the significant part of longitudinal compression gets converted into shear waves. When they are rapidly absorbed, the interface between a soft tissue and the bone is selectively heated. About cryotherapy, you will read in a PDF. Please pay attention. Your homework. Read a lecture and take the test after lecture in 2 weeks. And I will open the test for you tomorrow. And I will attach a lecture at PDF format today. And that's all. Thank you for your attention. And see you next lecture. Thank you.